faces here today, I see. So this is all about the project you'll be doing next week and 2 weeks after that. As I told you last time, the volume of the project has been at least not scaled up, so I guess it's a quite reasonable amount of work required. And also I'll give you some background material this week. Last week I didn't know a shit about this stuff, so we'll try to learn together. So, okay. Of course, this project is related to the global warming we are experiencing, and most researchers feel that or mean that, or they can't prove it, but that is the increased amount of CO2 in the atmosphere. That's the main cause for this temperature increase that we're seeing. And well, if I had been a young researcher and I had some theory about something, and I was going to the lab and getting my data, and my theory was that CO2 concentration correlated with global temperature, I would be, yeah, really happy about the result, because it seems to literally be the same graph, more or less. These data are, of course, quite old. It's almost 500,000 years back in time. So we can see, and all the data, I guess, have been collected by different means, like finding air bubbles in ice cores and analyzing the CO2 contents of those. We have this isotope ratio of oxygen, where you can kind of deduce the temperature when these minerals were formed and so forth. And using different number of techniques, they can kind of find out what the temperature has been and what the CO2 concentration has been. And you see there is alarmingly well correlated graph. The level of today's CO2 from 1960 to 2020, the last 60 years, you see that the amount of CO2 in the atmosphere has increased by more or less 25%. And it's much higher than it has been for a long time. I'm not sure how many million years ago you have to go back in time to find the same levels of CO2 in the atmosphere. So we're doing quite an interesting experiment on the Earth, seeing what's happening. Probably most of you will see much more than what I will see of the consequences, but they could be rather serious, of course. Yeah, so this is the reason behind choosing this topic. I mean, there are of course other, I'm not going to have a long talk about climate in general. I think this is the last slide about that. You have this Milankovitch cycles, which where there are three kind of geometrical issues related to how the Earth behaves in our solar system, which then affects the amount of sun power coming radiating at us. We have this precession, which is the change in the ellipticity of the track of the Earth around the sun. It changes this eccentricity due to the two large planets in our system, Uranus and Jupiter. They kind of affect our way around the sun. Then we have the obliquity, which is yeah, eccentricity. I guess that's the, I have actually, if you want to see a bit closer what these mechanisms are, I found a nice page, Milankovitch cycles and their role in Earth. So you have this changes in eccentricity, which of course affects climate, which has a 100,000 year cycle. then we have this obliquity, which is the axis which the Earth spins, which also affects the climate. And finally, we have this wobbling of this axis, which also affects climate. So I guess this is, but they can argue that it's mainly the CO2 content that really affects us. These are very long-term stuff. Okay, so today we'll look at this energy balance sheets that we're going to calculate, or energy balance between the sun, the Earth's surface, and the atmosphere. So, and a key player here is this black body radiation you may have heard about. That means that everything broadcasts radio waves. You broadcast radio waves right now, but they're invisible, of course, because they're in the infrared, low energy spectrum, where you can't see. The nice thing about this, this radio broadcasting, if you call it that, is that it's only dependent on the temperature. That defines the complete spectrum and the power of the radiation. So at the blacksmith, for instance, we can see that when it's heated up, some of these radio waves become into the visible band length, so we can see the actual radio waves coming, or light, equivalently. And that's what we're going to use for this model stuff too, because if you have a look here at this black body radiation, it's kind of a long history around it as well. Planck, in the year 1900, arrived at this formula for this, how the spectrum of a black box or a black body radiates. A black body is a kind of an idealized body that sucks everything, all light hitting it. And then it mixes in thermal equilibrium. You kind of have the atoms that vibrate, act as broadcasters, because vibrating electric charges, they make radio waves. And how fast these molecules vibrate depends on the temperature, which then gives kind of what type of radio waves we can expect from a radiating body at temperature T. This was a large problem at the end of the 19th century because the classical theory predicted this black curve here. And when we're approaching the ultraviolet part of the spectrum, that's the left of this visible light, it all blew up, so something went wrong. Planck theorized that these energy levels come in discrete packets without really believing in it himself, and arrived at that expression where we see this thing that I marked there. Typically it's the sum of a geometric series, where each term then is the discrete contribution of energy. So, and arrived at that formula, which fitted exactly to observations. But he didn't really realize the quantum nature of things until Einstein came 5 years later and said that light comes in packages, photons, at least in some connections. Okay, so this expression then gives us the energy per area, per solid angle. A solid angle, that's kind of a two-dimensional analog of the standard angle, because when you go around the circle, it adds up to 2 pi. It's really the ratio of the length of the arc divided by the radius. That's the angle in radians. And we have the analog for how big part of a sphere that we fill. That's the solid angle. And it's really the area of this part we cut out of the sphere divided by r squared, which is the square of the radius of the ball. So the total kind of angle for the full ball is 4 pi, since 4 pi r squared is the total area, just as 2 pi is the angle for the full circle. So really here we, to get the total power that this black body emits, we have to integrate over a hemisphere. If we imagine that we have we have a little plate here. With area A. And we are standing here to use spherical coordinates. Say we have a small part here, which has solid angle d omega. So that's the fraction of the full sphere multiplied by 4 pi. Then this black body here radiates. And if we view this black body from the North Pole, we will see the full area A. And radiation will be given by that formula for the frequencies. That's between, I'm not sure how to pronounce that Greek letter. Anyone? Call it V. V, and V plus delta V. Oh, where's the A? I forgot to put out the A. Is it A? No, it's the last. So if you are watching this plate from this angle here, its effective size will be this length. And if this one is phi, then this length, if this one has unit there, then this length is cos phi. So the actual area you watch from this part of the sphere is A times the cosine of phi. So that will be the effective area that radiates at the position we are at. So if you want to find the full energy or the full power, because this B here has energy per area, per solid angle. So when I multiply it by dV, we introduce per seconds because V is the frequency. So then we get from energy to power per. Yeah, so it's the full power that's emitted by this one. So if we integrate this B, V, T, and then multiply by A cosine phi, and then we have the area element here, which is for a sphere with unit radius. It's sine phi. And over the half sphere, we have, yeah, and then we need, of course. integrate over all frequencies. So that will be the power from black body. Why are we interested in this black body? Well, let's just peek at the next slide. This is the yellow part, is the energy at each, or the power at each frequency that's observed from the sun. And we see that this spectrum from the sun matches quite exactly the spectrum of a black body with a temperature of 5,778 K. That's how we can estimate the temperature of the sun from the spectrum it senses. The red part is what we receive at ground level when it has passed the atmosphere. So we see there are a lot of frequencies that are absorbed, in particular by water. We see that the role of CO2 seems quite small compared to the water. But water is something we always have there, and of course is a strong function of temperature, how much humidity there is in the atmosphere. But let's go back to our black body here. Okay, so if you want to do this, this will give us the power from a black body with area A. So if we divide out A, we have power, watts per area. So let's have a look at this integral. We see that we can move this E outside. And then we have, and we can take this integral just by multiplying by 2 pi. And we can concentrate on the last integral here, which is, let's put the A outside too. This is half sine of 2 phi. Yeah, so we get A. Yeah, and a pi on there. And then, so what will the answer be? Yeah, and this integral is actually 1. We get 1/2 of 1 plus 1. So this is pi A integral of Okay, so let's have a look at what B is. It's 2h, where h is Planck's constant. Maybe we should write that. C, speed of light. And K is Boltzmann's. Okay, this Planck's constant has a unit of joule seconds. That's because we have this energy equals hv for a single photon. Speed of light is of course speed. And Boltzmann's constant, that's joules per Kelvin. That's what energy is. Times T. Okay, so we have this formula, c squared, and then we have the frequency to the third power. You see that this is dimensionless in the exponent here. So that will be the total power radiated by the black body with surface area A and temperature T. Okay, yeah, let's just put stuff outside here. P A to H C squared. Yeah. Like that. Okay, so let's try to make this integral a bit nicer by changing variable.
Spørsmål?
Ja.
Ville det vært aktuelt å bruke Håvard som er på delproduktion?
I guess you could do that, but then you have to adjust all the time. So, well, at least this is what I said. So. But I know this modified Planck's constant is also in use. Okay, so then if we put x equals to the exponent here, hv kt, so then our integral becomes, okay, so let's just have all the constants. Okay, so we have dv, that's k times t divided by v. Same limits for the integral. And then we have v to the power of 3. Did I forget?
Yeah, h.
H, thanks. So, all the h power of 3, x to the power of 3. Like that. Finally giving p, a, yeah, and this h cancels to k to the fourth power, g to the fourth power, c to the second power. Yeah, and h to the third power. Like that. This last integral is, well, we can't calculate it by taking the antiderivative. It's called the Bose-Einstein integral. And actually it equals 6 times the zeta function of 4, which you can calculate, for instance, by using Fourier analysis in Math 4. This is pi to the fourth power divided by 15. And then we arrive at our formula, which of course has a name, and which we will use a lot. So it all adds up to a times 2 pi to the fifth power, k to the fourth power, h to the third power, c to the second power, and 15, and times temperature to the fourth power. That's the 6. It's the number 6. Which is, of course, interesting in relation to the prime numbers. So you can actually calculate the Riemann zeta function for even arguments, 2, 4, 6, etc. But the interesting thing here is that the total power radiated per area is proportional to t to the 4th power. That's a bit strange, isn't it? So if I double the temperature, I will 16 multiply my radiation with a factor of 16. Actually. And this is called the Stefan Boltzmann. And this constant here is then of course called Stefan Boltzmann. Constant. So this is more or less how we arrive at this formula, that the black body radiates energy at the power proportional to the 4th power of the temperature. It comes from integrating up this black body radiation distribution. Yeah, so as mentioned then, the sun is more or less radiating like a black body in thermal equilibrium at the temperature 5778 Kelvin. At least that's the outer part layer that kind of communicates with the rest of the universe. What the temperature is inside might be something quite different. And we see that water plays an important role as an absorber of energy. Actually, not all the sunlight that hits Earth will be absorbed. A lot of this sunlight, which is mainly high frequency, short wavelengths, compared to colder objects. Because if you had, you see that the colder the objects are, the lower, of course, is the energy they put out, but also the kind of the maximal value disappears and goes out of the visible spectrum. That's why we can't see the radio rays coming from you. But still, a lot of the spectrum is within the visible part, even at 3000 kelvins always. So when we see something glowing because it's warm, we only see part of the spectrum, the little part that goes into the visible part here. So next slide, yeah. And also you can see from this microwave background map, which is a snapshot of the universe 300,000 years after the Big Bang. It's a perfect black body. And from that we can also estimate the temperature of the background radiation from the spectrum. Yeah, just to show you that this black body stuff is quite universal on many scales. Yeah, so this we just derived now, the Stefan Boltzmann law. So, and this constant then is in SI units, it's 5 times 10 to the minus 8 approximately. That's kind of, say, more or less physical background of this formula that we will use a lot. We could write like that. Okay, so that's background for that stuff. For sure. I forgot to put on that. It's 1:45. So let's have a look at some crude modeling of the temperature on Earth. We have something called the solar constant, which is the energy that radiates from the sun per square meter, or the power per square meter. So we have the sun here, and the Earth here. After it travels 1 astronomical unit, isn't that the length to the sun? Then this power here is sigma naught, which is approximately so we're hit by something that has this energy level. It's the solar constant. And the solar constant that hits the Earth and hits an area of it doesn't cover, it doesn't hit the full sphere, it only hits the projection, which has area pi r squared, 1/4 of the area of the surface of the Earth. So at average, the surface of Earth receives, let's see this, sigma 4th watt per, I guess that's already included. Let's put it like that. One-fourth of that. Now we're talking about, say, zero-dimensional models that consider the kind of the average of the whole Earth. That will, of course, vary quite a lot from latitude, bredegrad, and other things. Now, everything isn't absorbed by the surface or the Earth. The best way of looking at this is we have Earth here, and we have high frequency radiation coming in. Then about 30% on average will be reflected, and 70% absorbed. So let's have a look at what happens if we don't have an atmosphere. Because since the Earth absorbs 70% of this power that is hitting the Earth, and we need to have a balance in the energy so the Earth doesn't get heated up. So the Earth has to emit long wave because it's much colder than the, let's call it T here, it's colder than the sun. So we get a different spectrum from the black body radiation from Earth than we receive from the Sun. So in a sense, we receive quite few high energy photons. That means that the entropy of the energy coming in is quite low. There's not so many states for the system. But we emit a lot of low energy photons out to space, balancing the energy that comes in, which has much higher entropy. So it really is an energy we need from the Sun. We need low entropy to keep ourselves a long way from equilibrium, being alive. When we're in equilibrium, we have rotten up. You know. So really the reason for needing energy all the time, because energy is conserved. Why do we need new energy? No, we need new low entropy. Okay, so the long way going out. So if we make up this also, let's define it. Alpha P is the average fraction radiation from the Sun. That is reflected. That is called the albedo. We also have local albedo, I'm not sure how to pronounce it. I mean, for instance, at the poles, there is white ice, so then a lot more gets reflected, so the albedo at the poles is much higher than where there is no snow and ice. For instance, we'll have a look at that in one example soon. So let's put up an energy balance sheet here. So if the Earth receives, the Earth has an area of 4 pi r squared, and as a black body, this is the power radiated out then, or the full thing here is this is the watt that is radiated out. This must balance then pi r squared, which is the area of the incoming sun that hits Earth, times the solar constant, times the so-called co-albedo. This is the fraction that is absorbed. So this gives the balance of, let's call this NW, and this is short wave. SW, balance of energy. So what temperature would Earth have now if the surface of the Earth was the surface that communicates with the universe, that gives out energy matching the energy we get in? We know the value of this is approximately 0.7, this 1 minus this co-albedo. This we know has been measured by satellites, for instance, what the solar constant is. So we can now solve for t squared, or for t. And if we solve this equation, it's quite trivial, we get t equals 254.6 Kelvin, was it? Which means that, and this is about, what is it, minus 18 degrees or something, Celsius. Yeah, something like that. So that means that our atmosphere is quite necessary for keeping up the temperature. Because without an atmosphere, the temperature on Earth would be minus 18 degrees on average. At least with this cold albedo here, but it will be even colder because then you get more and more ice cover. This cold albedo will go down and the temperature goes down. So if we had a totally ice covered, if you had ice covered Earth, and now I'm following this guy called North. I'll show you a reference to the article I've been reading. On that time, it's from the early 80s. They didn't know that actually snowball Earth had occurred. Now I think they there are several times in geological record that the full Earth has been covered with ice or snow. But then volcanoes have fixed things. Because when there is snow on Earth, no CO2 gets absorbed by the ground, by the rocks. So the CO2 concentrations build up quite much and then melt all the ice again. That's what they think at least. But in the 80s, they didn't think the Earth had been covered with, so he was wondering how could that be? It's a bit strange. So he was right. So, what time is it? Yeah. So if you have an ice-covered Earth, then this 1 minus alpha p would be, was it 0.30? I've written it down. 0.38, I think. I forgot to put up my notes. That means that a lot more of the energy from the sun is reflected and it will get even colder. So these are kind of this Stefan Boltzmann's law, enabling us to calculate things like this. And the solar constant and this albedo are kind of key parameters in the simplified modeling of the climate. Yeah, let's have a break and we'll look at something different afterwards.